Hello, we are going to start with our first video from Chapter 12, which is on 12.1, the fundamental counting principle and permutations. So we're going to jump right into a word problem. We have TGIF Fridays has a deal where you can order an appetizer, entree, and dessert for a low price, but you have to choose from a smaller menu than the whole thing. So you have a choice of two appetizers, spinach dip or potato skins. For our entree, you have three choices. You can choose a cheeseburger, barbecue chicken wrap, or bruschetta chicken pasta. And then last, for dessert, you can choose between Oreo Madness or vanilla bean cheesecake. What we want to do is we want to find out how many different meals you can make. So if you were to go back to Fridays every single Friday, you don't want to eat the same meal every single week. So we start off with our two options of the appetizer. We've either got spinach dip, or you can choose potato skins. From there, we have the same three options for our entree. We could have a cheeseburger, barbecue chicken wrap, or you could have the bruschetta chicken pasta. If you do potato skins, you have those same three options, so cheeseburger, wrap, or pasta. After you choose in your entree, you can choose your dessert, and each dessert option is either going to be the Oreo Madness or the vanilla bean cheesecake. So if you get the cheeseburger, you could get the Oreo Madness or the vanilla cheesecake. Barbecue wrap, same two options, Oreo or cheesecake. Pasta, you get the Oreo or the cheesecake. And now we jump down to the original potato skins. We can get potato skins, then cheeseburger, and then the Oreo or the cheesecake. The wrap, same two, Oreo, cheesecake. And last, our pasta with potato skins. Okay, so we have mapped out every single possibility. We count this up. We've got spinach dip with a cheeseburger with the Oreo Madness, that's 1. The spinach dip with a cheeseburger with the vanilla bean cheesecake, that's 2. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 different meal options. Now that was a lot of work. Let's say we had a bigger menu to choose from. You don't always want to have to write everything out longhand and waste all this time making this big diagram here. A shortcut for that would be our counting principle. We have two appetizers, so we've got two options for the appetizers. For the entree, we have three options: cheeseburger, barbecue chicken wrap, or the bruschetta chicken pasta. For our dessert, we have two options: the cheesecake or the Oreo Madness. So 2 times 3 times 2 gives us our 12 meals. A lot faster than drawing out that whole diagram. So let's say we had a bigger menu to choose from. As we just said, we have 7 appetizers to choose from, 13 entrees, and 2 different desserts. We multiply our options together. 7 for appetizers, 13 for entrees, 2 desserts, which means we have a total of 182 meals that we could take, or that we could make up from those different options. How many weeks will it take to eat every single one of those meal options? Well, we have 182 options, and there are 7 days in a week, which means it would take us a whole 26 weeks in order to get every single possibility from that menu list. And as we said before, this is going to be the counting principle. The counting principle says if one event can occur m different ways. So for our appetizer, it was either spinach dip or potato skin, so that would be 2 different ways. And other events can happen n ways and p ways, and you can do this for as many things as possible. And then the number of ways that all the events can occur is m times n times p times however many different events that you have. That will tell you the total many ways that you can rearrange those. So number 2, many states require license plates to have 3 digits followed by 3 letters. How many different license plates are possible? So sometimes you have to stop and think about it. Digits, some of you might be thinking, okay, there's thousands of options. If you think about just a digit, that's just one number. So digits run between 0 to 9. If you count 0 through 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, those are 10 different options. 3 letters, think about how many letters are in the alphabet. We know that there are 26 letters in the alphabet. So if we want to come up with all the different license plates, we have to think about all the different ways that it could happen. There's 3 digits and 3 letters. So our first 3 blanks are going to be contained by numbers. You have 10 options. 0 through 9, those are 10 different options. And then we consider our letters. It's followed by 3 letters, and there's 26 options for each letter. So we've got 10 times 10 times 10, taking care of all possible numbers for the number portion, and 26 times 26 times 26, which is taking care of the 3 letters. We multiply those all together, and we get 17,576,000 ways. So when you make up those license plates, those so many if you just do 3 numbers and 3 letters, and if you pay attention when you drive down the road, there's people that have 2 numbers, 4 numbers, 5 numbers. So think about all the different ways that you can write up those license plates. Part B, how many are possible if digits and letters cannot be repeated? So we still have 6 blanks that we are taking care of. The first 3 are still going to be taking into consideration the fact that we need 3 digits. But if we can't repeat, we have 10 options for the first one, 0 through 9. If we can't repeat that number, whichever number we choose, it could be a 4 or a 9 or a 7, whichever number is taken out is no longer available for our second spot. So instead of having 10 options, we now only have 9 options. Well, if I've taken 2 numbers out, for the third number, I only have 8 options available. When we go to our letters, we start with all letters in the bank. So there's 26. If I take one option out, I now only have 25 letters to choose from. If I take that one out, I have 2 already out, so now I only have 24 ways left to choose that letter. If I take out repeats, I've cut that number down from 17 million down to 11,232,000. Alright, number 3. How many 5-character passwords can be created if the first entry must be a letter and the last entry must be a number? Okay, so we first know that we have 5 characters. 1, 2, 3, 4, 5. It has to be, the first entry must be a letter. So if this must be a letter, that means that there are 26 options for that first piece. And the last letter must be a number, so that last one has to be a number. And we know from above we've got 10 options, 0 through 9. Which means we just have to figure out these 3 in the middle. If there's no specific requirements listed, then that means it could either be a number or a letter. Well, I've got 26 letters and 10 numbers, so there's 36 options for that middle one. Those middle 3 actually. If they don't say that it can't be repeated, or if you think logically about it, sometimes you can't repeat things. I'm not going to tell you you can't repeat them because it makes sense. If you're picking students for something, if I pick you, you're no longer available to be picked a second time. But when it comes to passwords and license plates, I can repeat numbers, I can repeat letters. So unless specifically said you can't, assume that you can. So when we type that into our calculator, we end up with 12,130,560 different ways we can create a 5-word or 5-character password where the first number has to be, or the first character has to be a letter and the last one has to be a number. Go ahead and turn over to the next page. We're now going to talk about permutation. So that was the counting principle. Permutations is dealing with ordering objects. And when you order these objects, the most important thing to remember is with permutations, the order or the rank does matter. So when we get into this, 8 horses are in a race at the Kentucky Derby. How many different ways can the horses finish the race? Assume there's no ties. So this is why we're saying order does matter. It matters who comes in first, and it matters who comes in second, and it matters who comes in third. If it didn't matter, there'd be no point in having the race. So we want to find out how many different ways can they actually finish. If we have 8 horses, then we have 8 spots that have to be filled in. 1, 2, 3, 4, 5, 6, 7, 8. For the first place, if there's 8 horses, there's 8 different ways someone can finish first. If the horse has finished, how many ways can we have second place? You can't have 8 ways because one horse is already finished, which means you have 7 options for who can finish second. If you have two horses that have already finished the race, that means there's only 6 options of who's left to finish third. So this is one of those places where you can't repeat. If a horse has finished first, there's no way that that horse can repeat and then come in 5th or come in 6th. If the horse has finished, they are now out of the race, and so forth. So if we take those out, there's 4 different horses left. There's 3 horses left. There's 3 horses, 2 horses, which means there's only 1 horse left to finish in last. So out of an 8-horse race, there are 40,320 different ways that those horses can finish. So think about that. If you ever go to the track and you're betting on those horses, how many different ways can the horses finish first, second, and third? So in the first one, we were looking at how many different ways can all the horses finish. So we wanted to look at who finished first all the way to who finished last. In this part, we only want to consider the first 3 horses. So we only have 3 blanks that we are talking about. If there's still the 8 horses, there's 8 different horses that can finish in first. That horse finished, so there's only 7 left for second, and only 6 left for third. So there are 336 different ways that the horses can finish first, second, and third. So permutations, really important. Most important thing that you want to take away is that with a permutation, it matters in the order in which it happens. Which brings us to our factorial. The factorial is a shortcut to solving the permutations. The way that this looks is an n, or whatever your ways are, with an the exclamation point is what we call the factorial. And when you break it down, it's n times n minus 1 times n minus 2 times n minus 3, and so forth until you get all the way down to 3 times 2 times 1 times 0. So up here, this was n, so 8 times n minus 1, which is 7, times n minus 2, which is 6, times n minus 3, which is 5. So it's just in descending order. Permutations of an object taken r at a time. The number of permutations of r objects can be taken from a group of n distinct objects is denoted by n factorial over n minus r factorial. So we're going to talk about this in just a second. What I want you to know is that all of this stuff is in your calculator. So if you don't have your calculator out, get it out. So we're going to use it in just a few minutes. So let's make sense of all of that terminology and notation that we just looked at. So let's look back at the horses problem. 8 horses are in a race at the Kentucky Derby. How many different ways can the horses finish the race? Assume there's no ties. Instead of doing 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, we can just do 8 factorial. Alright, so let's see where that factorial sign is on your calculator. So we type in 8, hit the math button. Once you hit the math button, you're either going to arrow 3 to the right, or if you just go left once, you will end up at the probability tab. And you can see down at number 4, number 4 is your factorial sign, that exclamation point. We hit enter, and we see that we get the exact same answer that we got the first time when we multiplied 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which doesn't seem as bad when you just have 8 things. But what if you're doing a 40 factorial? You really don't want to have to type in 40 times 39 times 38 and so forth. Our second question there is how many different ways can the horses finish first, second, and third? So it doesn't seem so hard to do 8 times 7 times 6, but if you wanted to use the factorial, that's where this equation is going to come in. N is the total number. R is how many times you want to permutate that. So in this case, we have 8 total horses. We want to finish first, second, and third. So that would be 8p3. So if we follow that formula, n factorial on top, our n is 8. So we've got 8 factorial on top. And then it's n minus r. We've got 8, we're taking away 3. So that's 8 factorial divided by 5 factorial. So we've got 8 math, arrow to left for your probability tab, number 4, divided by 5 factorial. And you see that you get 336, the same way we got up top by doing 8 times 7 times 6. Now you also could have just typed in 8p3. So if you look at the math button again, arrow to the left, you see that number 2 is NPR, which is the formula that you see right there. When you enter it in and when you choose to use this method, you could do 8 factorial divided by 5 factorial. You could do 8 times 7 times 6. All of those are valid methods. When you choose number 2, you've got to remember that you've got to type the n in first. So before I get to this screen, I'm going back to the home screen. I want 8p3, so I enter in the 8. Then I go to math. Then I go over to number 2 and type in R3. And once again, you get 336. So the only trick with this one is make sure that you hit the 8 or whatever your n is before you go to NPR. So let's try another couple examples here. For number 6, there are 12 books on the summer reading list. How many ways can you read 8 books? So if there are 12 books total, that is Rn, we want to choose 8. So that is 12p8. If you plug that into your formula, you get 12 factorial over 12 minus 8 factorial, which is 12 factorial over 4 factorial. I want you to go ahead and finish part A and then go ahead and try to do part B on your own. Okay, let's see how you did. When you enter in part A, again, you could have typed in this equation or you could have typed that in right there. You get 19,958,400. For part B, we're choosing 12 of 12. So 12 minus 12 gives us 0 factorial on the bottom. If you are doing 0 factorial, note that 0 factorial is just 1. So you're taking 12 factorial divided by 1. You end up with 479,100,000 1,600 different ways that you could read those books. All right, so one last page. How many different ways can we rearrange the letters in the word dogs? So let's go ahead and get rid of our calculator for now. Okay, that's better. So we have dogs, which means we have 4 different slots. We want to rearrange them. So we have D-O-G-S. We've got 4 different letters we can put in the first one. 3 different letters we can put in the second one, because we've already used the first one. 2 and 1, which is just 4 factorial, which is going to give us 24 different ways. Now we're going to look at ordering with repetition. Until now, when we have ordered events, repetition had no consequence because all of the objects we've ordered have been distinct. So when you had 12 books, or you have words like dog, D-O-G-S, each of those letters are different, which means you have distinct answers when you rearrange them. Sometimes objects are repeated, and then the permutations are not distinguishable. For instance, of the 6 ways we can letter the word, we have the word pop. We want to rearrange the letters. So we start with P-O-P, O-P-P, P-P-O, P-O-P, O-P-P, P-P-O. You've got your uppercase P, you've got your lowercase p. Well, regardless of uppercase and lowercase OPP and OPP, those are not distinguishable because P is being repeated. There's only 3 distinguishable ways that you can look at this, and that's POP, OPP, and PPO. So we have to take into account, well, what if I have the same letter twice? I want only distinguishable arrangements here. So if we have 3 letters and 2 are the same, the way we're going to rearrange this is there's 3 total on top, so it's 3 factorial. We're going to account for the 2 being the same, so we're going to divide it by 2 factorial, and we see that we have 3 distinguishable arrangements. This is going to be an excellent quiz question. So when we look at permutations with repetition, we have a new little formula. So the total of n objects factorial on top, and then how many times a letter or something is repeated on the bottom. Sometimes you only have one thing repeated, like we did with dogs. With pop. When we had pop, we had 2 P's. One letter was repeated twice. Sometimes you're going to have multiple repetitions. So we look at the number of distinguishable, is the key word there, ways in which we can order Mississippi. We've got M-I-S-S-I-S-S-I-P-P-I. So we've got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in Mississippi, which means we're going to have 11 factorial on top. What we have to do is consider all of the repeats that we're going to have there. So we look at M. We only have one M. Our next letter is I. We have 1, 2, 3, 4 different I's. We look at S. We have 1, 2, 3, 4 S's. The next letter we get to is P, and we've got 2 P's. So we have lots of repetition here. Total of 11 letters on top. We've got M only happening once. We've got I happening 4 times. S happening 4 times. And P happening 2 times. So we divide that by 1 factorial, 4 factorial, 4 factorial, 2 factorial, considering how many times each letter is occurring. We are only going to show that for the first time, M only happens once, and 1 factorial is just 1. So as a shortcut, you only divide by how many times each letter is being repeated. And when we type that into our calculator, we end up with 34,650 distinguishable ways I can rearrange the letters in Mississippi. All right, I know this was a long video. There's a lot to talk about with permutations and factorials and permutations with repeats. So make sure that you really have looked and paid attention to the fact that one thing that you have with permutations is that order is going to matter. And you have to consider, can I repeat something? If I repeat it, is it going to make it unique, or is it just going to be yet another thing that looks the same? So you really have to think about the problem that you're given and think through whether something's possible or if it makes sense.